Hello, everyone. Welcome to the session 3 of the Think Like a Physicist Clematis training program. I'm Sapu, a PhD student at the University of Oxford, and I'm very excited to be here with Libby, who will be leading the session today. So Libby is a fully funded PhD student at the University of Sydney, and she received the full-ride Pearson Scholarship at the University of Toronto, which is where she did her undergraduate in physics and astrophysics. For today's session in Astroparticle Physics, she will take us through the exciting topic of the mysterious invisible thing called the dark matter. So what exactly is the dark matter? How do we know dark matter really exists? Can we detect dark matter? And if so, how do we detect it? Right? And she will also take us through relatively simple concepts in physics like electricity to show one of the cutting edge instruments used in the search for dark matter. And she will also touch upon other exciting topics like superconductivity, electronics, and the uncertainty principle. So once again, thank you, Libby, for being here. I really look forward to the session. Feel free to take it from here.
Thank you so much for that introduction. And yes, I think that from here, I'll take it on and let's begin with the session. Hello, everybody. Thank you once again for that introduction. And now let's get right into the session. As it was just mentioned, this third session is going to be about astroparticle physics, more specifically, the search for dark matter. So through this presentation, we're going to, first of all, start by looking at what is dark matter. So what is dark matter made out of? So in general, just a general definition of what dark matter is. Then we're going to go on to some evidence of how we know dark matter exists. After that, we're going to go over some properties of a dark matter particle. So how do we know this is a dark matter particle? So what properties must it have? After that, we're going to go a bit into the detection methodology. So how do we go about detecting this type of particles? And specifically, we'll focus on one of the experiments that is called the SuperCDMS experiment. Okay. We're also going to dive a bit into the detectors of this specific experiment. And finally, we're going to go a bit over the current state of dark matter search, so just what's going on right now. Okay, so with that said, let's dive into this. And first of all, let's answer the question of what is dark matter? And the simplest definition one can give is pretty much that it is an invisible and hypothetical type of matter. Okay, now when I mean invisible, I mean that it doesn't interact with any wavelength of light. And when I mean any wavelength, I'm not just talking about the visible light, so what light that we can actually see with our eyes, but for example, all of the spectrums, so including ultraviolet and infrared. Now, what this means is that it doesn't interact with any wavelength, means that it doesn't interact with the electromagnetic force, okay? So that's an important property of dark matter. Second of all, something that I want to mention here is that I said it is a hypothetical type of matter. What I mean with this is that no dark matter particle has been experimentally found. Okay, so it's still a hypothetical type of matter. It is widely accepted, and that's because of the evidence that we're just going to see in a bit. So how do we know dark matter is there if it's still a hypothetical type of matter? The first example of evidence that we're going to see is something called the mass to light ratio. Okay, and for that, I'll like to begin answering this question by asking you guys if you could answer this question. So, where would you guess the majority of the mass of this galaxy cluster is? Okay, so do you think, based on what you're just looking at, do you think that circle B, circle C, or circle A encloses the majority of the mass?
So I have launched a poll, and remember this is anonymous, so we cannot see who answered what. So I encourage you to try. So using your intuition, where do you think the majority of the mass is in the picture?
Think of maybe like the light that is actually there.
Great. So all of everyone answered B.
And yeah, the answer would be B, right? Based on the amount of light, if you were to look at this, the circle B appears to be enclosing the majority of mass of this cluster of galaxies, right? Just because this has more light coming from it, right? Now, this is intuition-based, what most people would think, and it was what was thought by astronomers. However, when they actually carried the calculations to see where there was more mass in this galaxy, they found out that the measured cluster mass, so the entire mass of this cluster of galaxies, was not equal to what was estimated based on the luminosity of the galaxies in the cluster. So based on how much light we can see, okay, so let me put it this other way. Sorry, the amount of light that we see here does not account for all the mass that there exists, meaning that over here and over here there has to be some invisible type of matter. Thus the name dark matter. So That was one of the first observations that led to the proposal of dark matter, of the existence of dark matter. And in general, most of the examples, the other example we're going to see follows a similar logic. Now, the second piece of evidence that supports the existence of dark matter goes into rotational curves. And in order to explain rotational curves, we're going to look at the formula for rotational velocity in a galaxy. So this here is a galaxy, and the velocity at different points of the galaxy, so in point A or point B, is going to be determined by this equation here. Now, G here is just a gravitational constant. Then we have the mass distribution, which is dependent on R, which R is the distance from the center of this galaxy. So from the center of this galaxy to this point, all the matter that is encapsulated, so the mass distribution, okay? Now, something important to mention here is that based on the luminosity, so based on the matter that we can actually see, it is pretty much clear that all of the mass is concentrated at the center. There is mass as you go farther away from the galaxy. We still see some light, but not that much, right? And the farther you go, you can see that R would increase, right? And with that intuition, I'll ask you to answer these questions. Just which star would you expect to have a higher velocity, so a higher rotational velocity? Do you think if you're closer to the center of the galaxy, you should be going faster, or if you're farther away, you should be going faster, based on the formula here?
So I have launched a poll looking at the equation for rotational velocity. Which star would you expect to have a higher velocity? The hint is to look at the relationship between, the velocity, the radius, and the mass.
Okay, well, actually, the correct answer, based on intuition, sorry, the correct answer would be based on luminosity. Okay, so based on how much mass there is, we would expect it to be point B. And since some people are actually put A, I'm just going to take some time here to explain intuition of this. As I said, most of the mass is concentrated at the center of the galaxy, at the center of this galaxy. Okay, so the mass here, so this value is going to increase only when you're close to the center. The farther away you go, M is going to increase a tiny bit, but not as much as R. And as you can see, if R increases, so the distance from the center of the galaxy increases, the velocity is going to decrease. Okay, so with this intuition, we can actually plot what the velocity, rotational velocity is going to be as you go farther away from the center of the galaxy. So here we have rotational velocity, in kilometers per second, and here we have the distance from the center of our galaxy in kiloparsecs. This is just a measurement of distance used in astronomy, but the important thing to see here is that the farther away you go, you're going to have this decreasing slope here. The farther away you go, since, as I just mentioned, M is going to increase, but not that much, while R is going to take the lead and is going to cause the velocity to decrease. So this is what you would expect based on the matter that you're actually able to see. So based on the luminosity. Now, what was actually observed was something like this. So instead of seeing a decrease in the rotational velocity the farther away you are from the galaxy, from the center of the galaxy, it was observed that the velocity remained pretty much constant. So what is happening is that this is telling us that the rotational velocity is not lower at position A. So here star A will have a similar rotational velocity as star B. And if we go back and look at our formula, I said G is the gravitational constant, so that doesn't change. What has to change is the mass distribution. So there has to be more mass between the center of the galaxy and point A, more mass than the mass that we can actually see. So more than just regular matter. And just to convince you of this, here is an example of various galaxies. So each line that we can see here represents the rotational velocity of a different galaxy. And as you can see, the fact that there's so many galaxies that have this flat behavior at a higher radii, so far away from the center, is direct evidence of dark matter. Okay, so here this shows us that there must be more matter than actually meets the eye. Okay, so just by looking at this, you can see there's actually a lot of dark matter in our universe. Most of, if not all of these curves are pretty much flat the farther away you go. So with that in mind, let's ask ourselves, how much dark matter actually is there in the universe? Okay, so how much is there? I'll actually ask you here if anybody actually remembers. It was given pretty much away in the email, so how much dark matter in percentage what is there? So here you have ratio, and while you're answering that, I just want to mention that most of the universe is made of what is known as dark energy. I'm not going to dive deeper into that. That can be an entire presentation on its own. We can just think of it as the thing that is causing our universe to expand at an accelerating rate. So it is important, but it's not a focus of this presentation. So here, take a guess, please, of how much matter to visible matter to dark matter there is in the universe.
I've launched a poll. So as we can see on this pie chart, 68% is dark energy. But for the remaining 32%, how much of it do you think is dark matter? Is it 0% dark matter, 32% visible matter, 5% dark matter, and 27% visible matter? Is it equal? Is it 16% dark matter and 16% visible matter? Or do you think there's 27% dark matter and 5% visible matter? Or do you think the remaining 32% is dark matter and there's no visible matter at all? Okay, so I would end the poll here. So we have some people answering 5% dark matter, 27% visible matter, and we have some people answering 27% dark matter and 5% visible matter. Yeah.
So the correct answer actually is 5% visible matter and 27% dark matter. And just by looking at this, as you can see, most of the matter in our universe is actually made of dark matter, while visible matter is just 5%. So with that in mind, I have been talking about dark matter a lot, of course, but I have not specifically told you what makes up dark matter. Okay, so what particles are what makes up dark matter? And to begin with, the path of actually seeing what are dark matter particles, let's ask ourselves, could dark matter particles be any of the standard model particles? And what I mean with standard model particles are the particles that make up everything that is visible, regular matter. So everything that you see and everything that's actually part of regular matter is made up of this elementary particles, okay? And now what we're gonna do is we're just gonna take a tour over the different groups of standard model particles, and we're gonna see why they cannot be dark matter particles, okay? Now, first of all, we have quarks, okay? Now, cool fact about quarks is that they don't like to be alone. They like to be bounded together. Now, as you can see, quarks make up protons and neutrons. So these are just the same protons and neutrons you see at the center of your nucleus in an atom, okay? But quarks have charge, okay? So individual quarks have a charge. You might be thinking this is a bit odd for a neutron, but a neutron overall doesn't have a charge. However, the individual quarks that make up the neutron do have a charge. That just cancels out when they are all grouped together. Now, since they have a charge, they interact with light, okay? So they cannot possibly be dark matter particles. None of the quarks can be dark matter particles because they will interact with electromagnetic force. So quarks are out of the question. Now let's look at leptons. And before going on to neutrinos, I just want to mention that I hope some people recognize the lepton. It's just a common lepton you're familiar with. And we also have muon and tau, which are part of leptons. They're similar to electrons in the sense that they also have a charge. So they interact with light. They cannot be dark matter particles. And now let's go into neutrinos. Now, neutrinos are very interesting particles. They're very fast. And what I mean that is fast compared to the speed of light. And they're abundant. They're very, very abundant. However, they rarely interact with matter, okay? So you can think of neutrinos are actually right now passing through our bodies, okay? So there's a lot of neutrinos. One of the main sources of neutrinos is the sun. But just to give you an idea of how much they hate interacting with anything, let's see this example here. So a neutrino would have to travel approximately 0.75 light years, okay, to achieve a 50% chance of interacting with the nucleus of a lead atom. So they really do not like to interact with stuff, okay? And you might be thinking, doesn't dark matter also like to interact with stuff, right? So this is kind of similar. However, if we look a bit more into the complex properties of dark matter, something that is accepted of dark matter is that it doesn't travel really fast, okay? And as I just said, neutrinos travel really fast compared to the speed of light. So that is one of the major contradictions with neutrinos actually being dark matter particles, okay? Now let's move on to this other row here. So these are the force carriers, okay? And just as a quick question right now, I wanted to ask you guys if you could answer this. So photons are the force carriers of which fundamental force? So there's the four fundamental forces in physics, and so there's a poll, and if you could please take a guess or answer what are photons the charge carrier for? So which force do they actually interact with?
Yep, I've launched a poll. Okay, great. So everyone answered electromagnetic force.
Yay. So yes, everybody's right. So photons are the force carriers for electromagnetic force. Gluons are the same thing for the strong force, and sudden double bosons for the weak force, in short. Okay, so none of this can actually be none of the particles of dark matter or force carriers for dark matter. As you can see, they're already associated to other forces. And finally, we have the Higgs boson. Okay, I'm sure some of you might have heard of it. It is the newest addition to the standard model particle, and we can think of it as being associated to the field that gives mass to other fundamental particles. So this can be an entire presentation on its own, once again, but it cannot be a dark matter particle. Okay. So with that said, all we have set up until this point is that dark matter particles are not standard model particles. So we have pretty much ruled out all of the particles that we know of that exist as potential candidates for dark matter particles. Now, we have done this, so then what makes up dark matter? Along the way of doing this, we have described a few properties of dark matter particles. The first one being that it has to be neutral. It cannot have a charge, it doesn't interact with light, right? So aside from that, we have said that it's cold. When I say cold, I mean that it travels slow compared to the speed of light. It's stable, meaning that it has a very, very long lifetime. So it is not going to decay spontaneously, or it decays, but very, very, very rarely. Now, aside from that, it is almost collisionless. Okay, so with this, just to give an example of how collisionless it is, here we have a cluster which is known as the bullet cluster. Okay, it was formed when two clusters of galaxies collided, and it gets its name from the bullet-shaped gas that was left behind. So the pink that you see here is where the majority of the normal matter is, and its majority is hot gas. And then we have here in purplish bluish where the dark matter concentration is. Okay. Now the interesting thing of this collision is that when everything collided, when the two cluster of galaxies collided, none of the dark matter particles collided with each other, or like in general at all. So you have this entire clusters of galaxies colliding with each other that have dark matter, and still there's no outcome of dark matter interactions. So it is that's just to give you a sense of how collisionless it actually is. Okay, so since we have pretty much ruled out everything, what is usually done in this case is that a theoretical type of particle is proposed. And the main candidate, or the main particle that has been proposed in dark matter, is known as the weakly interactive massive particle, or WIMPs. Its name pretty much has the main characteristics of this type of particle. The first one being that it interacts weakly with regular matter. And when I say weakly, I do not mean through the weak force. Okay, so it's not associated with the weak force. In this case, it just interacts weakly with regular matter, and it falls in the massive scale of particles. And when I say giga electron volts, it's just a measurement of mass. And just to give an idea, this is a particle that would be approximately in the scale of protons and neutrons. So it's not as small as neutrinos and electrons. Okay, so it's this candidate is actually pretty big. Okay, so and now that we have set up what we're actually trying to look on, so our candidate, let's go into how we go about detecting dark matter. So let's go through the possible experiments. Now, before explaining this first one, so the collider methodology, I just want to say that SM here refers to standard matter, okay? So this diagram here is telling us how we can attempt to detect dark matter. In this first case, which is sometimes called like trying to make dark matter, we try to go from a standard matter to dark matter by generating dark matter particles through colliders. Okay. Another methodology that can be done is to try to detect dark matter directly. This methodology is also synonym by saying shake it, so we can try to shake things and identify the scattering outcomes that come from dark matter particles. Now, here, as you can see, we're staying within the realms of standard matter. Okay, so regular matter. Since we're gonna use standard matter, so a target, to get signals that are also in the realm of standard matter. So we're not trying to detect here dark matter particles themselves. Now, the last methodology is to try to detect things indirectly, or break things by searching for the byproducts of dark matter pair annihilation. So here we're trying to find out signals in terms of standard matter that come from dark matter interactions. Okay, now the methodology that we're going to focus mainly in this presentation is a shake it, and the experiment that we're going to see is a super cryogenic dark matter search. Now, we're going to take just a moment here, and we're going to actually break apart this title here to kind of understand what this experiment is based on. So the first thing is, well, the word super here just refers to the fact that this is a larger and improved version of CDMS. So there have been past experiments that were past experiments named CDMS. So this is the improved version. Now here, dark matter search. So this part here just telling us that it's a detection experiment. We're searching for dark matter, right? So pretty straightforward. However, the word that I expect to be new for most people's vocabulary is cryogenic. So what does cryogenic mean? It means anything that is related to the study of very low temperatures. And when I say low temperatures, I'm not speaking about like 0 Celsius or like -1 or -2. I'm actually speaking about millikelvin, so close to -270 degrees Celsius. So kind of around that region. And why do we need this? We need this because the detectors of this experiment are going to make use of a quantum phenomenon known as superconductivity. Okay? And now we're just going to take a step to understand what superconductivity is, since it's very important in this experiment. Okay, so what is superconductivity? Now, in order to begin this explanation, I will ask you to please answer this question. So it's pretty straightforward. So what property of a metal, so here we have a metal, okay, and a current is passing through this metal. So what property of this metal or material will cause the energy to be lost as the current passes through it? So if anybody would like to chat it, type in the chat.
I've typed in the chat what property of this material, in this case like metal, will cause energy to be lost as the current passes through it. So you could think in terms of like in physics, like in, when you're studying currents. Great, yes.
Resistance, yes. Somebody answered in the chat, and yes, it's resistance. As he mentioned, so yes, it is resistance. So metals have resistance. Okay. Yeah, so that's a property that's going to cause a bit of loss in energy. And now let's think about this. When the resistance is higher, we're going to have collisions between the metal atoms and the electrons. So all these metal atoms, they're going to be collisions which are going to stop the electrons from just passing through freely. Now, these collisions are going to generate heat. So that is how energy is lost. Okay. This phenomenon, when heat is generated as current passes through a resistor, is known as resistive or Joule heating. Okay. So I'm sure that some of you have seen this. So here we have a stove, right? And current is passing through this metal here, right? The wire of the coil there, and it is generating heat. So this is an example of Joule heating. Okay. Now, when you increase Joule heating, this is equivalent to increasing the resistance of the material. So you can think of it this way: the more heat there is, the more the atoms of the metal are going to vibrate. The more they vibrate, the more collisions are going to be. So the harder it's going to be for the current to actually pass through this metal. Okay. Now I've talked about heating this metal, but what happens if we actually cool the system? What will happen to the resistance if we cool the system? Will resistance decrease or increase?
So remember, we are cooling the system. So when we are cooling the system, what happens to the resistance of the metal?
Okay. So it is actually gonna, so what happens when we cool our system is it's actually gonna decrease. And so I guess I'll take just a moment here to explain why. And resistance will decrease because when you cool the system, you're removing energy from it, pretty much. Now you're at lower temperatures, there's gonna be less collisions. Okay, so things are gonna stop vibrating. So the atoms are gonna stop vibrating so much inside the metal, and the current is gonna be able to pass through it without so many having to collide so much. So there's not going to be that many collisions stopping the current from just passing freely. So there's less resistance. Okay, so that's what's happening. And in some materials specifically, if you cool them to low enough temperatures, the resistance vanishes. These materials are known as superconducting materials. Okay, in superconducting materials, there's no resistance, so nothing is going to slow the electrons in the metal. So they're going to be able to just go freely through it as if there were not there was nothing there. Okay, so that is the principle of superconductivity. Okay, and now that we have, hopefully we have learned that.
Is it okay if I interrupt a little bit?
Yes, yes.
Yeah, so the way I think of resistance is it's like going through a crowded room. And when there's a lot of heat, you could think of like people are so energetic. If I'm an electron and I'm supposed to pass through a very crowded room, that's very energetic, like dancing. It's going to be really hard to pass through. So that's why when there's a lot of energy or there's high temperature, the resistance is a lot, right? Because it's going to be hard for me to pass through. However, let's say in that very same crowded room, but none of the people in that room has energy. Okay, so that means the temperature is decreasing. So because everyone is staying still, if I'm an electron wishing to pass through that crowded room, it's going to be really easy because everyone is not moving. They're just staying at the same place. So that's how I think of it, like in terms of resistance, right? So lower temperature means there's less energy, there's less collision, and the electron can easily pass through.
Thank you for that explanation. I think, yeah, that's a very good way to actually explain that in an analogy. So hopefully that is clear for everybody. And now we're going to go into the SuperCDMS experiment. So we're going to take a look at the detectors. Okay, so now here I'm just going to take a step back and refresh a bit. So what are we actually looking for? We have our dark matter candidate, we know these properties, and we're saying we're trying to detect it directly. So what we're actually trying to do is identify the scattering outcomes when a dark matter particle collides with a target nuclei. So when I mean target nuclei, I mean an atom of regular matter, okay? Now, what the scattering outcomes that we're trying to detect are signals, okay, that are going to be in three forms. So we're going to try to detect signals in the form of vibrations that come out of the collision, in the form of light, and in the form of a charge change, okay? In more scientific terms, this is referred to as phonons. So phonon signals are synonymous to vibrations in vibrations that come out of this collision. Then we also have scintillation, which is light signals, and ionization, charge change signals. How are we going to go to detect the signals? So how are we going to actually detect the signals? And for this, I'm going to divide things in three parts. Okay, so first of all, like I said, we need something that acts as a target material. We need something that's going to be able to collide with the hypothetically the dark matter particle, okay, and generate a signal. Second of all, we're going to need a sensor. We need something that's going to be able to sense those signals. And finally, we need something like an electronic electronic system that is going to allow us to read those signals. So it's not only enough to actually be able to sense them, we need to be able to collect that data in something that we can read out nicely, okay? So we need a readout signal, okay? So at this point, I have described like this experiment and how we do it, like how this detector works. However, I hope some people are wondering, what happens if something that is not a dark matter particle collides with the target materials, okay? Because dark matter particles are not like, well, hypothetically, are not the only thing that are gonna wanna collide with this. There's a bunch of other particles. At the beginning, I said that neutrinos actually are just passing through us, right? So there's a lot of backgrounds that we have to account for. So how can we reduce noise in the systems? And the first precaution that is taken to reduce noise in this type of detectors is, first of all, SNOLAB, so where the actual experiment takes place, is 2 kilometers underground. So it's at a mine. The experiment takes place at a mine that is 2 kilometers underground. And this is done as a first layer of shielding. So in order to shield the detectors from high energy cosmic ray particles and radioactive decay byproducts. So these were things that will also cause collisions and cause signals such as phonons or scintillation or ionization. Okay, so we want to really shield this detector as well. Now, the second type of shields that we can use are actual shields that you would imagine by enclosing our sensor and our target material inside layers of copper can, inner and outer neutron shields, and PB gamma shields. So all of this is done to effectively block radioactive backgrounds, so different types of backgrounds. I'm more than happy to go into a bit of detail at the end of the presentation, but for now, we're just going to keep on going. So this is just to give you an idea of how shielded these detectors actually are. Okay. And finally, the last layer of shield that is actually used is the fact that inside the shield, everything is cryogenically cooled. So everything is at very low temperature. So superconducting temperatures or close to superconducting temperatures. And this is done in order to reduce thermal background, okay? So once again, we're trying to reduce another thermal background. And those are the three main shields that are used. Okay, now with that in mind, now let's take a closer look at the three parts of our sensor. So the first thing, as I said, we need a target material, right? Something that is going to collide with our dark matter candidate. And for that, in this type of experiments, they use germanium or silicon crystals, okay? So once again, this is a bit repetitive, but still, what we want to capture the electrical or the vibrations and electrical signal from particle collision. So once again, we have our dark matter particle is going to go collide with the nuclei, in this case of these crystals, and it's going to release a bunch of signals. Now, like I said, we're going to focus on what measure phonons, but just to give you an idea of why we want to measure, for example, charge, it is because by measuring all of these types of signals, we're going to be able to also differentiate from common background matter. So by having all of these values, we're going to be able to tell what is obviously not dark matter. Okay, so we've gone over our target, what is going to be our target. Now let's go over the sensors that are used here. Okay, and the sensors that are used in this experiment are transitional edge sensors, and they work based on superconductivity. So the phenomenon, as we previously saw, that some materials have, that when cool to low enough temperatures, their resistance vanishes. Okay, so as you can see here, when they're cool, it's just gonna vanish. Now, here we have our TS sensors, okay, and we're gonna take here step by step to see how they actually work. Okay, so in principle, what's gonna happen, same case as last time. So we have our germanium and silicon substrate, our target, our target nuclide, okay, and when dark matter go in there, they're gonna collide with the nuclide and they're gonna release. In this case, we're trying to detect phonons, so they're gonna release vibrations. Now, this here is what is known as an aluminum fin. All that this is an antenna that's going to gather those phonons, okay? So it's just something that's going to grab all those phonons. Now, inside this aluminum fin, these phonons that have been gathered are going to break electron pairs, okay? And at this point, I hope this raises some concerns or at least some eyebrows of, wait, electron pairs? So what do you mean with an electron pair? Intuitively, it doesn't make sense, right? Because electrons have same charges and same charges do not attract. Now, we're going to take a step here, a little detour, to understand what are these electron pairs and why are they in this aluminum fin. Okay, so the first thing to remind you is that everything in this place is cryogenically cooled. So anything in this sensor is going to be cryogenically cooled. So this aluminum fin is at a superconducting temperature. Okay, so we have our superconducting aluminum, and what we're going to see inside it, here are the aluminum atoms, and as you can see, they have a positive charge. Okay, since they're at a superconducting temperature, they're not going to be vibrated. They're not going to be moving at all. They're just going to stand still, letting the electrons pass by. But because electrons have a negative charge, what is going to happen is that as they pass by, they're going to slightly attract the positive charge aluminum atoms, okay? And what this is going to do is that it's going to generate an area, like an area where there's going to be a slight positive charge, okay? Just because of this electron attracting all of those positively charged aluminum atoms together, they're going to clump and create an area where it's a slightly positive charge. Now, what this is going to create is that, what this is going to actually do is that when you have another electron pass by, it is going to be energetically favorable for these two electrons to pass by. So because we're in an area where there's a slightly positive charge, this new electron is going to be attracted to it, and it's going to form a pair with this other electron, okay? These are known Cooper pairs, and as I just mentioned, they occur because at superconducting temperatures, it's energetically favorable for electrons to pair up. There is no other energy that's going to cause them to actually separate as they would in a regular material, right? So there's nothing that prevents them to happen in this case, okay? So those are what are known as Cooper pairs, and they're going to be what breaks inside the aluminum fin when a phonon is captured by the fin. As I said, the phonon is going to introduce a bit of energy, and since Cooper pairs exist in a superconducting state when there's nothing to disrupt them, in this case, the phonons are going to disrupt that the bound that they have, and they're going to break. When they break, they're going to release energy, okay? And this is going to heat up this piece here, which is known as the TS resistor, okay? So our resistor is going to heat up, And as we learned before, if we heat up our resistor, the resistance is going to increase. Okay, so at the end of the day, what we're actually going to be able to see, what we're actually going to be able to see is that when we detect a photon, there's going to be an increase in heat, meaning an increase in resistance in our TS resistor. Okay, and how the beauty of this sensor is the fact that it's going to be able to auto-regulate itself. So the more photons you detect, it's not going to continuously increase in heat. Okay, so it's going to actually go back, and as I'm going to show in a bit, what we're actually going to be able to see is a pulse-like signal. But for that, we kind of jump into the fact that these are called transitional edge sensors. And the transitional part comes from the fact that this sensor, so this specific resistor, as I mentioned, is cryogenically cooled. But what we're going to do is that we're going to hold it. So here, this is a zoom version of the plot that we previously saw, okay? And what we're going to do is that we're going to make sure that it is cooled such that it is just before, so it is at a steep slope, just before the resistance vanishes. So this is what is known as transitional width, okay? So it is a region within the temperature here that a very small change in temperature, so just a tiny millikelvin change in temperature, is going to cause a significant change in the resistance of this material. Okay, so we're going to maintain it in the steep slope such that we're able to get a significant change in resistance. Okay, so as I just mentioned, this is going to allow us to have this pulse-like signal at the end of the day. Okay, so this is what we're going to detect when we detect a photon. Now, another important principle of transitional edge sensors is what is known as negative electrothermal feedback. As I previously mentioned, there are sensors that are going to auto-regulate itself. Once a photon is detected, it's going to go back to the resistance it had at the beginning. So it's going to go back to that sweet transitional stage. And this happens because when we have an increase in temperature, so let's say we have detected a photon, okay, the temperature is going to increase, the resistance of our TS resistor is going to increase. But as you can see here, we have a bias voltage. So we're going to have a current that is flowing through the circuit, okay? And if the resistance increases, the current flowing through this resistor is going to decrease. So as we learned before, if current is going to decrease, our Joule heating is going to decrease, okay? Which is going to cause temperature to decrease too. And finally, resistance is going to decrease. So it's kind of this auto-regulating system that is going to allow us to get this pulse-like signal, okay? So that's why we actually have this, which is a voltage a bias voltage that is going to allow us to maintain our TS resistor in this nice transitional stage. Okay, so that is it when it comes to our actual sensor. And now we're going to go on to the final part of the detector, which is the electronic readout system. Okay, and here, just to give you an idea what's happening, the resistor we saw here, it's the same one. So this is the same one we saw in the previous diagram. Now, the reason this just has an arrow is because it's a resistance, it's going to change. So it's not a constant resistance. And here, and yeah, so that's pretty much it with that. And the goal that we have with our electronic system is that we want to get a highly precise voltage signal. We don't want a measurement in resistance, which is what we have at this point, okay? We want a measurement in terms of voltage, because that is going to allow us to actually get more information, the information we want out of the phonon signal that we initially had, okay? And in order to understand this, I understand what is happening in this circuit specifically, I'm going to ask you to think about this very simple circuit, okay? So basic electronics. If R1 is greater than R2, which path will the current take through the circuit? So if R1 has a much higher resistance than R2, where will most of the current flow through? Is it going to be R1 or R2?
Yep, just give me a second. Actually, just feel free to type in the chat for this one.
Yeah, exactly, right? R2. So current is going to take the path of least resistance, right? So current is going to prefer to flow over R2 than R1 because it has a lower resistance, okay? Now, this is the same concept that we're going to apply here, okay? So here we have, first of all, we have our warm electronics. When I mean warm, sorry, I should have mentioned this before. I mean that they're not at a superconducting temperature or they're not cryogenically cooled. Everything that is cold here refers to cryogenically cooled electronics. Now, as we saw before, current is going to go through the path of least resistance, right? So when our TS resistor is at that transitional stage, its resistance is going to be very, very low, so close to zero. And However, when we actually get a phonon and it heats up, all of a sudden our TS resistor is going to have a much higher resistance than this other shunt resistor. Okay, so at the beginning, most of the current is going to flow through this arm here. Okay, but when we detect a phonon, this resistance is going to increase, meaning that most of the current is going to change path and go this way. Okay, now why we have this coil here is because we're going to take advantage of this change in current flow, and we're going to try to detect the magnetic field change that is caused by this inductor. So at the end of the day, what we have here is we have our coil, okay, and when current passes through a coil, it generates a magnetic field, okay? And this is actually what we're going to want to detect, how the current changes the magnetic field based on how the resistor here changes. So we need a detector, a very, very precise detector that allows us to actually measure the changes in magnetic field. And these detectors are known as superconducting quantum interference devices, okay? Now, there is three main principles that rule them, okay? But in simple terms, SQUIDS are just magnetometers, or they're pretty much in charge of translating a magnetic flux into a voltage signal. And remember how at the beginning I said that what we actually want is a signal in terms of voltage, right? So these are the devices that are going to allow us to get a voltage signal, okay? But first of all, to understand SQUIDS, we have to understand its three principles. The first one of which we have already covered, so we have already covered superconductivity, but now we're going to jump into what are Josephson junctions, okay? And then we're going to go into magnetic flux quantization. Now, in order to understand Josephson junctions, we have to understand a very important quantum phenomenon, which is quantum tunneling. But first of all, let's look at things this way. Now, electrons, just like photons, behave as a wave and as a particle. Okay, so classically they behave this way. So just like, for example, a ball bouncing off a wall, but they also have properties of quantum mechanics, meaning that they also act as a wave. Okay, so as you see here, they can also act as a wave, meaning that they are also governed by the uncertainty principle. And the uncertainty principle, all it tells us is that you either know the momentum or the position of your electron, but you cannot know both at the same time. Okay, so that's uncertainty that comes in quantum mechanics. Okay, and electrons are going to take advantage of this principle. Okay, and when we have a very defined momentum, so when momentum is well defined, it opens a chance for the position of this electron to be on the other side of the wall. So since we know the momentum pretty well, we cannot know the position also pretty well, okay? So there's a slight chance that the electrons are actually going to tunnel through the wall. And in order to have a better understanding of how that works, now, in order to have a better understanding of this, we're going to look at the probability wave of our electron. So this is just a wave that's telling us where it is most likely for the electron to be a different position. Okay, so it's more likely that the tops here are going to represent where it is most likely to find our electron. Okay, and in this case, I'll ask you to picture this. So we have a probability wave and we have a barrier here. Now, remember I said the uncertainty principle, if we know the momentum really well, we're not going to know specifically with a lot of precision where the electron is. This is going to open the possibility for the electron to actually be inside this wall. Okay, so it's going to be, and it can actually be inside the barrier that we have here. Now, if the barrier is thin enough, the probability is going to drop, but it's not going to, the barrier is not going to be thick enough such that it erases all probability for the electron to just tunnel through. And as you can see here, we're going to get a small probability that the electron actually is on the other side of the wall. So this is what is known as quantum tunneling. It's a phenomenon that occurs of the fact that electrons can actually tunnel through, for example, in this case, a wall, right? And still have some probability of existing on the other side. Okay, so I guess that now we take a 5-minute break before moving on.
If anyone has any questions,
Yeah, feel free to ask anything. We can go back to any point in the presentation.
meanwhile, if anyone has questions, feel free. So basically, the idea is that if I understand correctly,
Mhm.
the hypothetical dark matter, which until now we are not able to like get hold of it, right? That's how I
Yeah.
understand. But this
Mhm.
somehow collides with this thing, germanium and silicon.
Yeah, so the target nuclei, yeah.
Okay. And then when it collides, it produces phonons, which is a form of vibrations, correct?
Yeah.
And then when it forms a phonon, so does Cooper pair normally exist without the phonons, or Cooper pairs is formed once the phonons like activated? Is that it? Did I
So
interpret correctly or no?
yeah, I think I understand your question. So I'm just gonna take it back. So when the material is superconducting, you will have Cooper pairs. Okay, so
Right.
and this aluminum in this case, it is at a superconducting temperature, so there will be Cooper pairs regardless if there's a phonon signal or not. So Cooper pairs are like a property of superconducting materials. So they're all just going to be floating around there. And when the phonon comes here, it in short is going to break those pairs, which releases energy.
Right.
And
Because when phonons, it basically provides energy to the aluminum fins such that the atom starts colliding with each other and Cooper pairs won't form anymore, right?
yeah, so Cooper pairs are going to break.
So one Cooper pairs break, does it increases heat on the TES?
It's gonna, yes, so it increases heat, but that heat is gonna be gathered here. So you
Right.
will still have more Cooper pairs in the aluminum fin. Still gonna be a superconducting temperature. But when in short terms, when it's broken, it's gonna translate the phonon signal into a heat signal that's gonna be absorbed by the TS resistor.
Right. And then when you get the heat in the TES, it increases the resistance.
Yes. Yes, we're like at the range. So here we have the resistance, right? And the temperature plot that we saw before. And here this is assuming into it. So just before the resistance vanishes, we're gonna have a very steep relationship between temperature and resistance, right? So just because of the slope here is so steep, a very small change in temperature, so millikelvin change in temperature, is gonna cause a relatively large change in resistance,
Right.
right?
And that
Such,
allows us to have a really, like, just a
yeah.
very small change of temperature can basically build this big pulse and making the detection quite sensitive, right?
Yeah. So yeah, so that's the initial, yeah, that's the beginning of it. As we'll see later on, like, well, just in a bit, we do need like squids to actually be able to detect things because you need more, first of all, you need more precision, like more precise way of measuring this. And resistance is not gonna tell you the information you need about this collision.
Right.
So
Really cool. And the idea that you have this pulse is through the
mhm.
negative electrothermal feedback, correct?
Yeah,
Which kind of what you explained.
the reason, yeah, no, the reason that this doesn't overheat and just continues. The reason the resistance here doesn't just keep continuously increasing when we get photon signals is because we have a bias voltage and we're gonna auto-regulate this. So because there's always a current flowing through it, we're able to have negative electrothermal feedback. So it's just pretty much regulating itself um, to go back. So such that the resistance can go back to where it was before. If we want to think of it one way, we can think about the resistance. So there's a small change in temperature, the resistance goes up, okay, and because of electrothermal feedback, is then gonna go back down to
Mhm.
where we want it to be.
And what's the implication if it keeps heating? Like once it
If
goes
it
out of the range, what would
if it goes out of this place, then it doesn't, like, you can no longer have like the same relationship you have here. So if it's like, for example, here, right? Where, sorry, you're seeing the pointer here, you're not longer gonna have that large change in resistance, right? If you keep heating it up, it's not like it's gonna, this only works because you're at a very steep slope here.
I see.
So
I was saying so it's because the phonons or the energy is so small, that's why you need
mhm.
such a sensitive measure, correct?
Yes, so the energy is very, very small. Like I said, dark matter particles do not like to collide. Um, and in general, the collisions that you get out of this are not like huge collisions. Not like, I'm not talking like any explosion, like kind of thing. So what you actually get is a change in millikelvin. So this is a way to actually convert like something that's small as millikelvin to an actually measurable signal.
Oh, I didn't notice the millikelvin. That's really, really small.
Yeah, no, it's a very, very small signal that you actually get. So, like, this entire process and this detectors are designed, most of the detector in general is designed to amplify the signal as you go through, right?
So just for one more minute, I would like to ask a question about, or maybe I guess clarify
Yes.
quantum tunneling, which I think is a very fascinating topic. So, just to recapitulate how I understand it, and again, I'm not an expert in this field, but I'm trying to interpret what you say. On the left here, or on the left side of this slide, the electron, we think of it like classically as a particle, correct? And when we think electrons as a particle, we're looking at a classical realm. And in the classical realm, as a particle, it cannot go through the wall. It will just bounce off,
Yeah, like classical mechanics cannot explain the behavior of electron as a wave.
right?
That's pretty much
But
that.
when electron acts somehow as a wave, it exhibits quantum properties,
Yeah. So
right?
the wave properties are explained by quantum mechanics, not by classical mechanics.
I
Yeah,
think.
so momentum, when I say momentum, I mean energy, or we can think of also related to the velocity. So you can know like how fast or where the position is of the electron, but you cannot know both at the same time.
Okay, yeah, that's it. I think we can move on to SQUIDS, Josephson function.
Yeah, pretty much. So yeah, so last thing I said was mentioned about quantum tunneling, and the reason you actually have to understand this is because Josephson junctions are pretty much just two pieces of superconducting material separated by an insulator layer. So this insulator layer is analogous to the barrier that I showed before. So the barrier that we have here is pretty much, it is pretty much synonymous to having this insulator here. And in Josephson junctions, what we have is we're going to have, instead of the electrons tunneling, we're going to have the electrons pairs tunneling through our barrier here. Okay, so what is going to happen is that the current, so supercurrent, is just it's just a term used for the current, not of like individual electrons, but electron pairs, so Cooper pairs. Okay, the critical current here is a current that you can have as long as you can have while not having a voltage. Okay, and finally we have this that is a phase difference. Okay, and when I say phase difference, I mean phase difference between the superconducting waves. Now, as we know, since electrons have properties of waves, waves have phases, and this is the difference between the phase of the electrons in this side and in this other side. Okay, so here the main thing that I kind of want to just have you guys remember is the fact that the supercurrent, or the current flowing through this through the Josephson junction, is dependent on a phase change. Okay, so that is the main thing important about Josephson junction. So it is dependent on that. Okay, so that is the idea of Josephson junctions. And the last concept that we have to understand if we want to understand SQUIDS, it is what is known as magnetic flux quantization, which in very simple terms means that magnetic field can only exist in discrete values. So here we have two examples. This one you can see here, there's a mismatch. So here there's a phase mismatch. So this is out of phase, and it's not a physically valid state. We want a state where everything is nice and we do not have a phase difference. So everything encloses nicely. Okay, so it's just that idea. Now, I'm going to do my best here to explain SQUIDS, how SQUIDS function. SQUIDS are very complex devices. If anybody wants to interrupt at any point, please feel free to interrupt me as I'm explaining this. And it's not entirely necessary to understand how SQUIDS actually work to understand how this dark matter detection experiment works, but I'm going to do my best to explain it. Okay, so in SQUIDS, we have first of all, we have our two Josephson junctions. Okay, so we have one Josephson junction up and one down in our superconducting loop. Okay, and we're gonna pass a current through it. Just like in a normal circuit, since both of them have pretty much the same resistance, there's no much difference. Half of the current is gonna go up and half of the current is gonna go down. Okay, now remember that we're using this type of devices to translate a magnetic field. Okay, so when there's a magnetic field passing through our loop here, there's going to be a current generated. Okay, so as you can see, J here was going to be the current generated because of the magnetic field, and this part of it is going to oppose the initial current that we have, while the other half is going to actually increase the current that we had here. Okay, so as you can see, in one side of our loop here, the current is going to decrease, while in the other one is going to increase. Okay, now recall, as I just said, that we do not want a phase mismatch. We want everything to be nicely and in phase. Okay, when we have this, when we have our loop here, since we have magnetic flux quantization. And recall how I mentioned that a change in phase is proportional to a change in the supercurrent. So because we have our Josephson junctions here, okay, when there's a change in phase, such as one that can be induced by this magnetic field, okay, there's going to be a change in the current. supercurrent. Okay, so what our squids are gonna do, or what we can think of it how what they're doing, is that they will regulate the current in this loop such that you are able to maintain a flux quanta. So you're able to maintain something that doesn't have a phase mismatch as this here. You want something that is in phase. Okay, so this is, so I'm just circling this because I think this is a really good way to see it. We want to maintain something in the units of a flux quantum. Okay, and yeah, so that is mainly what is going to happen. So what is actually changing inside the squids is the current. The squids are going to send a different current depending on what is needed to maintain this. Okay, now it is by probing this current, so there's going to be a change in current, and we're going to actually, from the change in current, be able to measure a change in voltage. Okay, so that is the principle of how squids work. Now I'm going to move on tiny little detail that we also have to be aware when it comes to squids, and that's the fact that they have, as you can see here, a periodic relationship between voltage and flux. So when I mean flux here, I mean magnetic flux, okay? And as you can see, for one value of voltage, we can have various different values of flux, magnetic flux, and we do not want that, okay? We want actually a linear relationship, not this type of periodic relationship. So what we're gonna do is that we're gonna lock squids. So we're gonna make it such that we only get values in this region here, okay? And in order to do that, we use another magnetic field in order to lock them. So how this actually looks is that we have our squids here, we have the same circuit as we had before, and we're gonna use another coil to generate a magnetic field that is only gonna allow us to get values in this region of this periodic relationship. So for one value of voltage, we're just gonna have one value of flux, of magnetic flux. Okay, so that is what is happening here. There's also a bunch of electronics when it comes to amplification, and also actually being able to generate the signal that we need to lock our squids. But this is pretty much it. Now, the arrow that you see here is where you would actually read out the final signal. And at the end of the day, what you are actually going to be seeing is something such as this. So here we have amplitude in terms of voltage, and here we have over time. So the phonon, so what we're actually going to be seeing is just a pulse similar to the one we saw in resistance, but this pulse is going to tell us a value in terms of voltage. Okay, now I just, as a disclaimer here, this example here is not like an actual detection of dark matter. Dark matter has not been detected yet with this experiment, but this is what happens when you actually probe, when you actually test if the channel is working. Okay, and also I guess that I know that I wanted to say, I've explained all this, and this is only one of the channels that you can have. In reality, this experiment has, as you can see here, various channels. So there's a lot of TS resistors that are gonna be on top of our crystal. So just to give you an idea of how big this actually is. So it's not only one detector per like crystal, there are many detectors per crystal. So, okay, I know that was a lot, but to just begin wrapping things up, let's just think of what's next. So I've just told you that we have not detected dark matter yet. So let's take a look of what is going to happen. So what is actually happening in this type of dark matter detection experiments. So just a bit of an overview. Here, what we have is a plot that is going to show us, first of all, what is known as the WIMP nucleon cross section. So this is just telling us how interactive our dark matter candidate is. Okay, so as you can see, the closer you get to what is known as the neutrino floor, and the neutrino floor is just a space where we know we're going to detect neutrinos. Okay, so pretty much at this point, it is going to be very hard to detect dark matter once you pass this floor cloud. But we're not going to focus on that right now. We're going to focus on this line here, which is the SuperCDMS, okay, which is telling us that it can detect WIMP, so dark matter candidates within this that have a specific cross-section, so interaction rate, and have this specific mass. Remember at the beginning I mentioned the WIMPs are in the giga electron volt scale in terms of mass, but they're in a range. So depending on where specifically you want to detect, you create different types of experiments chartered to that kind of WIMP particle. Okay, so the SuperCDMS is right here. As you can see, the goal is pretty much to go lower and lower up until the point that you reach this this pretty much limit, if you want to think about it that way. Okay, so at one point when you actually go down here, it's really hard to detect dark matter. Right now, the current search of dark matter keeps on going, but yeah, no, we would just have to wait up to see what happens in the future. But with that said, I know this was a lot and it's a bit dense, but I thank you all for actually going through this, and thank you so much, yeah, for attending.
Yeah, it's just fascinating stuff, dark matter research. It's pretty sci-fi almost because dark matter, like you can't see it, but quite a lot of evidence, as you have shown with the mass to light ratio and the using rotational velocity. Is that correct? So yeah, very cool. And yet it's still very hard to actually come up with dark matter. So just to clarify this last slide, so all of these are ongoing projects.
Yeah, I was just gonna say that they use different methodologies to detect dark matter, but in general, it's kind of like, for example, xenon, it's the same idea but with a different material. Similar idea but different material. Yeah.
Oh, I see. That's really cool. Also, for the audience, if you have any questions, feel free to ask them. But for the next 5, 10 minutes, I might just chat about dark matter because why not? But before we go there, I wanted to talk about post-session activities really quickly. So the idea is that after every talk, it's always nice to have a scientific discourse because like when you go to conferences in research and things like that, to talk to scientists, in some ways, that's quite a nice practice and is a good skill as well to think about some of these important issues. So on our Discord, we have questions, critical thinking questions designed by Libby. And there are kind of three types. One is thinking questions. Another question is annotated bibliography, which is just a way to summarize a research paper. So in this case, it could be like on dark matter. And we always ask people to reflect. But again, this is up to you. But I think it's just a nice way to learn and engage in a scientific discourse. And Libby or I will engage. And maybe you might talk with your peers as well. Yeah, these are the questions that we would post soon. Maybe you want to talk about it a little bit or?
Okay, so yeah, no, sure. So the first question is mainly targeted to people who are interested in how electronics work. So in this question, I mainly wanted people to think or maybe question themselves of what causes a lot of noise within the readout system, which is the electronics. As I previously mentioned, um, a lot of care is taken to shielding this type of detectors, right? But you have to have the electronic system there. And at one point, that is also going to be a source of noise. I'm not going to specifically say why, but that is something really important that has to be considered. And yeah, so mainly that. Now, when it comes to the neutrino floor, I briefly just mentioned that neutrinos are really annoying in terms of background. So they're the most annoying type of background when it comes to detecting specifically WIMPs, so this type of dark matter candidate. But I just wanted you guys to think about a few of the characteristics that actually make them such a bad background. So like more specific, like in detail. And finally, dark matter distribution. So in this presentation, like I've mainly spoke about the direct type of a direct detection methodology. There also exists two other methodologies. There's a lot of experiments in those areas too, but direct detection is mainly favored for a few reasons, and I just wanted you guys to think of why maybe you favor direct detection methodologies instead of the other two methodologies, or like what advantages does trying to detect dark matter directly bring forth. So
Oh, very interesting questions. You have worked in labs related to that. Actually, in your undergrad, you kind of did this, right? The direct
yeah.
detection methods. You want to go a bit of how your experience was, or what do you do when you were working on like direct detection methods? What was your role as a researcher?
So my role as a researcher was working with this specific triangle that you see here. So with the feedback system, my role was to create an electronic system, well, an electronic circuit that is specifically designed to lower the noise that comes out of this specific piece of electronics. So um, pretty much what I did was trying to, I don't want to give too much information away because it's pretty much the answer to the question of noise. Uh, but what I can say is that I had to think about how we're going to convert the signal, because at the end of the day, we want a digital signal, okay? And most of the old electronics used in this case were a lot of mechanical things. So for example, okay, I guess I'll just give away one part of that. When you actually have switches, for example, that are manual, just by like moving like a switch in a circuit, you're going to create a tiny bit of noise. even if you don't do it, like you're not supposed to do it, of course, while you're actually trying to detect something. But even if it's just like a mechanical switch, it's going to cause a bit of noise. Okay, so my job was try to redesign this such that everything can be controlled through a computer.
Oh, okay.
I pretty much worked with this little triangle that you see here. So that was
Wow.
my job.
And was it fun?
It was fun in terms that you actually get to create electronics. So like I got to solder a bunch of things and learn a lot of about this. But yeah, as you can see, I was in charge of this little triangle here, which is a very small part. But in general, this work, and I think in this field goes this way. There's a lot of like most of the work goes into actually see how you read out the signal and how you're able to actually amplify it to get like a precise like signal readout, right?
Yeah, because you're dealing with such, well, it's kind of very hard to detect, firstly, I would assume, and second, you're dealing like very small, like how I understand is photons is very, very small. Like you're dealing with
Really
millikelvin.
Kelvin, yeah.
So wow, that's very interesting. And you know that graph that you showed, how much work goes into, analyzing those data? Like I know you haven't worked directly with that, but
Mhm.
based on, anecdotes and what you hear from your colleagues, do you know how much it takes to come up with like graph, the one with the
Mhm.
voltage and different sensors?
Um, in general, like I have seen a bit of like when I was does you mean like this, right?
Yes, that one, yes.
So in general, there's a lot of work, first of all, on analyzing noise. So first, I think that's one of the main things that you have to make sure that the channels that you're reading, so that they do not have that they're not very noisy channels. Um, I have seen a bit of the raw data sometimes, uh, not specifically of this entire circuit. Okay, so I've seen data that collected by SQUIDS. And just by looking at it, I can tell you that there goes a lot, like there's a lot of work in between what you actually get, like the raw data, and what is actually published at the end. Um, just like in general, like this is not only in the case of detecting their matter in general, there's always a long process between actually processing your data. And you don't only because you don't only you cannot not only show that, you have to show, at least from my understanding, that your channel is not very noisy, right? You have to show that everything is working properly along the way.
Very cool. And I was wondering, there are several ways in which you prove that dark matter definitely exists, and you've shown two.
Mhm.
Do you know any other ways?
Yeah, we can definitely go over some other ways. This being a third, I was going to present this as a third proof, but the third example that we can actually look at to prove the existence of dark matter, it is through gravitational lensing. And just to give you an idea, just to go over that, first of all, I'll ask you to picture this. So we have a quasar, which is just an extremely luminous active galactic nuclei. Okay, so it's just a very bright source of light. Okay, and generally, there's nothing in between that quasar and us. So from Earth, light is just gonna travel directly through it. So light is gonna go from the quasar to Earth. However, if we have a galaxy in between, okay, what we're actually gonna see is that light from this quasar is not just gonna go directly, it is gonna bend. Okay, so as you can see here, this galaxy is bending the light. So because this galaxy has a mass, it is a massive galaxy, it is gonna bend the light that goes towards Earth. Now, the bending of light goes all the way back to Einstein's theory of relativity. I'm not gonna specifically go too much into it right now, but you can think of this kind of as a lens that is gonna bend light towards Earth. Okay, so what we're actually going to see is instead of just seeing one source of light or one big source of light, we're going to see 4 points of light that are going to appear. Okay, so this quasar is going to appear as 4 points because this galaxy in the center here is going to bend those points of light, those sources of light. So what is coming? Okay, and why am I actually mentioning this? This is the effect of gravitation. So this is what is known as the gravitational lensing effect. And through this method, we're able to see how massive a galaxy is. So just by seeing how much light is bent or curved, we can know how massive that galaxy has to be and where the mass is actually concentrated. Okay, and a beautiful example of this is the bullet cluster, so the one we've seen before, right? And here we can use gravitational lensing to find out where the concentration of mass actually is. Okay, and once again, we saw before, the concentration of mass does not overlap here with the majority of the normal matter. So the majority of normal matter is actually this pink stuff here, which is hot gas. Okay, and dark matter is actually to one side. So here's actually the concentration of dark matter that we're seeing. Sorry, the concentration of mass. Okay, so the fact that the concentration of mass and where we actually are able to see dark regular matter is means that what is actually here is dark matter. Okay, so through gravitational lensing, we're able to know that here is where majority of the mass is, and since majority of the mass that is visible to us is at the center, we know that here there's dark matter. So in general, like the proofs of dark matter when it comes to astrophysics and astronomy are just gonna tell you that what we're measuring does not match what we're seeing, if that makes sense.
Right. So the idea is we would normally expect the expected mass to align with what we see, which is the visible mass. But
Yeah.
always the results that we get, it seems to be like, oh, there's actually some mass in some dark areas that shouldn't have
Mhm.
been there in the first place. And it seems
Yeah.
like, right, all of the three evidence that you show kind of point to that.
Yeah, no, so just to make it clear here, the coloring here is just so that we're able to see what is happening. Like this purplish color is just to show you where the concentration of mass is. Like we don't actually see this purple like color when we actually look at this cluster of galaxies.
Right. And
Yeah.
gravitational lensing is basically just a tool to map the amount of mass in a
Yes.
galaxy, right?
Yeah, pretty much. Yeah. It's a tool that is used. Yeah. I will be sharing some of the links of the papers and a bit more information to Discord. Anybody who's curious, there's actually very good books that go over dark matter, the
Oh,
existence of dark
okay.
matter. And they explain this in a lot more detail. And yeah, so and some really cool videos.
Yes, there are definitely quite a ton of resources on dark matter. Great. Thank you so much, everyone, for being here. Thank you, Libby, as well, for going through what a journey this is. I'm grateful that you went through all of the concepts. So thank you, everyone. Have a great day.
Thank you, everybody. Bye bye.
Clematis Research Empowerment Hub. Empowering research for everyone.